Hello, I'm Kira Ragazzo, and I'm going to talk about the implementation of a vapor-liquid equilibrium and vapor purge model for scale-up of a transfer hydrogenation. So I'll talk about the transfer hydrogenation reaction first. We'll go through reaction kinetics, which are heavily dependent on the palladium on carbon catalytic performance. And then we'll talk about the initial scale-up we did from lab to kilolab scale, which is where things went awry and we had very long reaction times. And then further understanding of the deactivation of the catalyst, where we were able to implement a model that predicts catalytic performance in order to finally have a successful scale up with some new scale parameters. So I'm part of the chemical process development group at Bristol Myers Squibb. We work to develop robust small molecule processes and scale up to provide clinical supply. So I was working on the synthesis of a late-stage intermediate with a heterogeneous palladium on carbon catalyzed transfer hydrogenation. We are trying to remove 4 CBZ protecting groups from the limiting reagent by using a palladium on carbon catalyst and a hydrogen donor in solution. So this means that the hydrogen donor provides hydrogen to the reaction and you don't have a hydrogen gas anywhere in the process. And then we have the product that has some amine groups on it. We have a byproduct of carbon dioxide, and we have a hydrogen donor related byproduct that doesn't really affect us. So transfer hydrogenation was used here because it enables flexibility and provides safety in manufacturing. So sparging is necessary for conversion on a vial scale, as we learned quickly. In the reactor to the right, you can see that the carbon dioxide being formed in the reaction can hang around in solution and not be fully purged into the headspace. So the procedure here is that the catalyst is heterogeneous. It's slurried in a solvent. In a separate reactor, we have the limiting reagent and excess hydrogen donor. And then that gets dissolved up, no reactions occurring because we don't have the catalyst surface to react on. You heat the primary reactor to the reaction temperature and then feed in very quickly the starting material and the excess hydrogen donor. So our initial experiments were on a 50 milligram vial scale. The purple bars here on this chart indicate the range of reaction times seen for each condition. So with each iteration of control moving down the chart, we've seen a reduction in variability. When we performed this open to air, we performed 8 runs and we saw a variability of 6 hours to just terminating the experiment at 48 hours. That incredible variability was due to not purging CO2 from the liquid phase. So this is confirmed pretty much by vac inertion before the reaction, not really reducing variability that much. It helped us complete the reaction, but we still saw reaction times from 2 to 17 hours. That variability is not scalable. So we hypothesized that the vac inertia beforehand was reducing oxygen in the system, which can participate in a side reaction with the hydrogen donor and form water, thus reducing the amount of hydrogen donor that can go towards the desired reaction. So that pushed some of the experiments to very low reaction times of 2 hours, but we still saw variability because something else was going on once the reaction started with the hydrogen donor available. Sparging the reagents before the reaction happens also leads to pretty slow reactions of 7 to 8 hours, and we've seen this reaction happening at 2 hours already, so we knew that something could be done to improve performance. Sparging reagents beforehand, similar to the vac inertia, reduces the oxygen available for the side reaction, but it doesn't help in purging the carbon dioxide. So we're still having slower reaction due to carbon dioxide inhibiting the catalyst. And then finally, sparging to clear the carbon dioxide byproduct from the batch definitely helped us out. That really reduced reaction time, so we got end of reaction at 2 hours because we were purging that CO2 successfully. So when we moved to the 250 ml scale, we saw that carbon dioxide is still affecting us. So in both of these runs, we were using the same nitrogen sparge rate, the same pretty aggressive catalyst loading and temperature, which is why the 800 RPM case finished very quickly in under 1 hour. But the 300 RPM case saw an initial reaction rate that we expected, and then in less than 5 minutes, it settled into 0th order kinetics that were essentially stalled. So the limiting reagent stalls when mixing is insufficient, clearly. The hydrogen donor is still present in excess at the end of the stalled runs, so we know it's not about the reagents available. And carbon dioxide is known to poison palladium in CBZ deprotections. So we took a run that had good mixing and sparred CO2 instead of just pure nitrogen into the reaction, and that stalled the reaction just the same as the 300 RPM case. Carbon dioxide can poison the reaction. And mass transfer is then critical to reaction completion. Purging the CO2 from the batch is critical. So taking this good case where we saw good performance with 800 RPM, then we looked into the mass transport coefficient, KLA. If we kept constant KLA across different batches, different sizes, all lab scale, we got reproducible results in lab. So carbon dioxide was adequately purged via nitrogen sparging to ensure that mass transport was not rate limiting. If we stayed above the threshold KLA, we're always in the kinetically limited regime instead of the mass transport limited regime. So we kept KLA constant using dynochem to achieve the same reaction rate with varied scale, impeller type, agitation speed, and sparge rate. We got the same rate constant with varied starting concentration with first order consumption of the limiting reagent, as you can see over to the left. And we also saw consistent temperature effect with the Arrhenius equation over on the plot to the right, where you can read the activation energy off of the slope. The temperature effect is relatively small here, so we didn't get the typical improvement of reaction rate with increased temperature, but we saw very consistent results. So this showed us that we have a reproducible process on the lab scale, and we scaled that up to 5 liters in lab and still saw good performance. So we thought this process was ready for the kilo lab. So initial scale up saw deactivation of the catalyst yet again. We saw good kinetics in the first 5 minutes, where we see the IR dramatically drop by limiting reagent, and then level off into 0th order kinetics, where the reaction's just going to take way too long when we expect it to take under 3.5 hours. So note on this plot that the limiting reagent by IR only goes down to 50% conversion. In the reaction time we expected, we saw less than 50% conversion. So this 5x scale up did lead to 0th order kinetics, even though we scaled by KLA. And we hypothesized that this is due to headspace turnover. So looking back at the reaction in the reactor over to the left, you see that you have nitrogen sparging into the reaction, and then you have carbon dioxide being formed in the liquid through the reaction, and then reaching some equilibrium, if the KLA is sufficient enough to do so, with the headspace. And then the headspace gets purged out through the vent through that same nitrogen sparge. So if we look at headspace turnover time, that increased significantly because in lab, the headspace turnover is very small, 3 minutes, which is the headspace volume over the sparge flow rate. When we go to the kilo lab, the sparge rate flow rate is not scaled directly. So we saw a headspace turnover at 20 minutes on scale, which means that we're not actually purging carbon dioxide from the headspace. So KLA is enabling us to reach an equilibrium between the liquid and the headspace, but the equilibrium concentration is way too high still. So the Henry's law constant for carbon dioxide is too high for the reaction to go well. So the next plot coming up is day 3 of the reaction. So we work in a single shift facility, and then we cooled the batch and held it overnight. and then resumed a second day, still saw 0 with kinetics and didn't complete, and then we resumed a third day after cooling overnight again. So that's why this plot is broken up from day 1, because you have those cooling cycles and it doesn't really follow that 0th order kinetics the whole time. So looking at this plot, the y-axis then goes from 50% conversion down to full conversion. And you saw that at the 12-hour reaction mark, that's taking out the time that we're cooling. That's just at elevated temperature with sparging. We're at 12 hours. We still had 7% limiting reagent remaining. At that point, we vacuum cycled, where we pulled vacuum and then backfilled with nitrogen 3 times, and then saw quick conversion down to full conversion of the limiting reagent. So we saw that vacuum cycles are an effective fail path, which further proves that carbon dioxide in the headspace is our problem when we try to scale up. So if you remove carbon dioxide rapidly with vacuum cycles and then reestablish the equilibrium by resuming the sparge, you can get full conversion. But in order to not rely on that fail path, we built out a model in MATLAB. So the MATLAB model couples kinetics and mass transfer. It assumes first order consumption of the limiting reagent and carbon dioxide generation based on stoichiometry, which you can see as the 4K in the differential equations over to the right. It does not model the region where reaction is mass transport limited, because in those cases where you have 0th order kinetics, those reactions are way too slow to be practical to us. So we want to stay out of that zone completely through this model. The inputs are scale, volumes, temperature, KLA, solvent ratio, which determines the Henry's constant of the system, and rate constant, which we took from lab data. And then the model calculates the carbon dioxide generation and purge from the batch and from the headspace. So you can see all those curves over to the right, the consumption of the limiting reagent, the growth of our product, and then the yellow curved, it's the dissolved CO2, which eventually gets purged through equilibrium into the headspace, which then gets purged out of the entire reactor. So that's the purple curve. So we basically want to control the dissolved CO2 maximum during reaction by controlling KLA and headspace turnover. So we're looking at this yellow curve and taking the maximum there. And we're going to sweep it across KLA and headspace turnover to get to this plot, where the model can predict the maximum CO2 level during reaction across a whole range of conditions. I'm plotting the failed scale-up reactions that we initially saw that weren't controlling headspace turnover, that first one at the 20-minute mark, and then also some failed lab reactions, and then on the top left corner, you can see our operating range, where if we have sufficient KLA and low enough headspace turnover time, you can get successful reaction. And that diamond in that quadrant is finally the successful reaction. So after we plotted this curve, I saw that I would want to keep KLA above 0.02 and keep headspace turnover below 5 minutes. And then I got that successful reaction at the same scale that we were not successful in the Kiel lab previously. So some conclusions. A typical scaling parameter for gas-liquid mixing is KLA, but for reactions that generate gaseous species, the efficient mass transfer can still lead to equilibrium concentrations that inhibit a reaction if there is insufficient purge from the headspace. So headspace turnover time is an appropriate secondary scaling parameter to add in to make sure that you're purging whatever generated gaseous species are coming into the reaction. And we can have holistic kinetic modeling of gaseous impurity levels in the solution and the headspace to provide appropriate mixing scaling parameters. And this model was successfully implemented on scale up for us after an initial slow reaction that was only scaling KLA. It allowed us to add in the headspace turnover and get a robust, quick reaction. So our model accurately predicted reaction times and could be applied to other reactions where catalyst inhibition is a risk as well. So I wanted to thank the team that worked on this with me. Fed, Zhangping, Ronald, and Sean are all co-authors of this work, and then other members of the product development team are listed as well. So thank you, everyone. Thank you for listening to my presentation, and please reach out with any questions.